Very much for the lovely introduction. So I would like to thank the organizers for and once again the organizers for inviting me to give a talk in the seminar. So I'm going to talk about my joint work with Katja Sagerschnig, who's also my colleague in Center for Theory of Physics. The paper was supposed to be on arXiv this week, but it seems like we need another week or two to finish things. We study sort of a class of geometric structures equipped with assuming that they have an infinitesimal symmetry. So we denote towards the end of the talk, if I have time, I will mention what this class of geometric structure is. But we call them parabolic quasi-contact cone structures. So there are a bunch of cones on a manifold, and we assume they have an infinitesimal symmetry, and then we characterize this class with an infinitesimal symmetry in terms of another geometric structure on the leaf space of this infinitesimal symmetry. So this is, and the characterization is purely local. So this is what we're going to talk about today. I'm going to talk about. So such results, they have been appearing in many other works. For instance, one of the famous works is the work of Kahn and Schwachhofer. They study something called special symplectic connections, which include the famous class of Bochner-flat Kähler metrics. And they showed there's a one-to-one correspondence between Bochner-flat Kähler metrics on a manifold and then flat CR structures on another manifold with one dimension higher. So this Kähler is obtained as a leaf space of the infinitesimal symmetry of the flat CR structure. So there's a one-to-one correspondence between flat CR plus an infinitesimal symmetry and this class of Bochner-Kähler, Bochner-flat Kähler metrics. In fact, any dimension. Any dimension. Flat CR structure means that it's locally the quotient space of SU of any signature, P plus 1, Q plus 1, mod out by the appropriate parabolic. So it's, in fact, this is like this sort of flat CR is the special case of the more general phenomenon that is, again, local in any CR structure. So integrable almost CR, these are called CR structures of hypersurface type. If you fix a choice of, if there's an infinitesimal symmetry, then there's a one-to-one correspondence between such classes and Kähler structures on the leaf space. So if you start with a Kähler metric on a surface, you can actually go backwards by a process called contactification that we're going to see later on and get CR structures with a choice of infinitesimal symmetry.
But the symmetry is a true symmetry,
yes.
Not just...
No, it preserves the CR structure, the complex structure, yeah. Yeah, the fact is, if you have an infinitesimal symmetry, it's always almost everywhere transversal to the contact distribution. That's in fact crucial in doing so. Yes. So this is, in fact, I mean, where we are coming from is that I'll say in a moment. So this is sort of, again, perhaps one of the most well-known cases of such type of results. And this was generalized to a larger setting in a series of papers by Chap and Salach. And they made like a one-to-one correspondence between a class of structures called parabolic contact structures with an infinitesimal symmetry and another class on the leaf space of this infinitesimal symmetry they refer to as parabolic conformally symplectic structures, which includes this sort of parabolic conformally symplectic structure. They include, for instance, Kähler structures, and this parabolic contact structures, they include, let's say, almost CR structures in particular. So this is sort of some history, some motivation of, so what we're going to talk about is to sort of generalize this work in a sense by considering sort of a class of structures that includes, in particular, conformal structures. So, for instance, to give an example, start with a Riemannian manifold. Then, on the product space, you can cook up this natural Lorentzian signature metric, and it has a killing field. In fact, well, depending on how you want to define it, I'm going with the conformal class of this metric. And there's you can view this killing as a conformal killing in particular. And this is like a way of starting from some geometric structure on a manifold and going to a dimension one higher manifold, and then having a conformal structure with a choice of infinitesimal symmetry, perhaps the most well-known case. So by conformal class, I mean the class of Lorentzian metrics that are proportional to this G tilde. So this this vector field preserves the conformal class, in fact, preserves the metric. And another observation is that if the Riemannian metric you start with has constant sectional curvature, then this conformal structure is flat, conformally flat, locally. So this is the type of result we want to go. We want to generalize this. So what we want to do is that we want to see how we can construct, in particular, all conformal, strictly pseudo-conformal structures. So not positive definite, strictly pseudo-conformal structures with symmetry. This type of characterization we want to arrive at. This is a picture that I'm going to explain what it is. So you can think about it as a Lorentzian conformal structure. These are the null cones at each tangent space, and these red lines are null geodesics. And there is a transversal hypersurface, which you can identify with the leaf space of the infinitesimal symmetry. So the infinitesimal symmetry, these are the dotted lines are the integral curves of an infinitesimal symmetry. And this transversal hypersurface, you can identify it with the leaf space of the integral curves of the infinitesimal symmetry. So what happens? I want to give the main steps of our construction that we're going to talk about. To do this characterization we want to do, it's essential. The first step is to, instead of working on the manifold n+1 dimensional manifold with the conformal structure, to go to the so-called sky bundle of the conformal structure. So the sky bundle is the bundle of celestial spheres. So the bundle of projectivized null cones. There are these null cones, and you projectivize them. So you get a bundle of quadrics, actually spheres, on n. And they're projective quadrics. So the fibers are n-1 dimensional. So you get a 2n dimensional bundle of quadrics, of spheres, actually, in the Lorentzian case. But it can be any signature. And it turns out we first have to identify the geometric structure here. So forget about this and just work with the induced geometric structure on this bundle, this sky bundle, we call it. So it has a filtered structure we're going to discuss. And then most importantly, it has something that is almost like a contact structure, because contact structure is on odd dimensional manifold. Here we have an even dimensional manifold. So this is called an even contact structure or quasi-contact structure. This is the first step in doing this characterization. The next step is to see if we have a conformal killing field, let's say zeta, then naturally this zeta lifts to the sky bundle and preserves this filtered structure on this sky bundle. So it will become an infinitesimal symmetry of the sky bundle, and more importantly, it will be transversal to this quasi-contact distribution. So this is the second step that we'll talk about. The next step is that now that it's transversal almost everywhere to this quasi-contact distribution, we consider the leaf space of this infinitesimal symmetry, and then we see that we can identify the tangent space of this leaf space with this quasi-contact distribution. So therefore, we see that there's a geometric structure induced on the leaf space of this infinitesimal symmetry. This is the third step. In fact, this geometric structure, you can see it in this picture. So if you have an infinitesimal symmetry, these null geodesics will see that, you see, null geodesics are geodesics along null direction. So if you go along the infinitesimal symmetries, null geodesics are projected to paths, these green curves on this so-called leaf space. So instead of having an analog of, the null geodesics are projected to a distinguished family of paths. For instance, geodesics of a Riemannian structure. So there's a sort of a so-called path geometry on this transversal. So at each point along each direction, there is a unique path that passes. And they are sort of projection of null geodesics of this ambient conformal structure. So there's a path geometry, but in fact, it's more, it's sort of augmented. How is it augmented? Because it remembers that it's sort of null geodesics of some conformal structure. So we're going to define exactly what it means by an augmented path geometry. The fourth step is to realize, and this is actually the most unexpected one for us, that just we realize what we've done so far fits into something extremely well known and classical that other people have done, namely the fact that this sort of paths that come here, they're not just any path, they are variational. They are extremal curves of some first order variational problem. So these paths are variational. In fact, there's like geodesics of some Lagrangian. This Lagrangian might be a Riemannian metric, might be a Finslerian metric. We don't know. It's just a non-degenerate Lagrangian. And there's not a unique Lagrangian. In fact, there's like up to a divergence equivalent. So you can add like a total differential to the Lagrangian, plus an extra condition. So this sort of Lagrangians allows you to have sort of defined in a way some form of unit sphere bundles on the quotient space, but there's a drift. Usually there might be a drift. So you can identify these unit sphere bundles as like a section of the null cone at each point. So these are some ways of interpreting. And this is we're done. So we have shown that conformal structure with an infinitesimal symmetry results in some variational path geometry. So some geodesics of some Lagrangian with some extra differential condition we're going to talk about. So we started from conformal, we went downstairs to some geometric structure, and now we reverse the construction. We show a process called, it's very easy, quasi-contactification. We show that if you start with any such geometry, this variational path geometries, this paths that are very extremal curves of some Lagrangian, you can always, exhaust all conformal structures, pseudo-conformal structures with a choice of infinitesimal symmetry. So this way we get a one-to-one correspondence. Yes? So this yes, exactly. We actually see when, downstairs, what are the conditions, differential conditions that results in, let's say, null symmetry. So basically, instead of working with conformal structures with an infinitesimal symmetry, you can only work on these geometric structures downstairs. So they're equivalent, and they control when they arise from a null symmetry, when they arise from a null symmetry that is orthogonal, integrable, these sort of, with an orthogonal foliation, this sort of thing. So what do you mean by augmented? We're going to define. There's an augmentation, meaning that it has an additional tensorial object attached to it. It's not just a bunch of paths that at each point along each direction, there's a path. There's another auxiliary tensorial objects attached to these path geometries.
So the leaf in the space of the integral, correct?
Exactly. Yes. So you can identify it with a transversal hypersurface.
Okay, but are you assuming it is a manifold, or
it might be non-Hausdorff, but in a sufficiently small neighborhood, we always know that and away from singularities, when things vanish, we can always work in a sufficiently small neighborhood that things are, Hausdorff and smooth and nice. No, exactly. We avoid them. And in fact, thinking what happens when there's a singularity is actually quite interesting, but we're not, yeah. Okay. So to just state the result before going into showing these steps, I first want to say what it means by sort of these augmented path geometries. We'll refer them as variational orthopath geometries. So they're nothing but, just think about the following, that you have Lagrangians, first order Lagrangians, non-degenerate, and you want to solve the equivalence problem of Lagrangians up to divergence equivalence, meaning that you allow multiplication by constant and addition of a total differential. But for us, the way we encounter this sort of geometric structures, if you remember from the previous slide, is by sort of, we have some curves and they arise as extremals of a first order Lagrangian. And this Lagrangian sort of, you can write it as a variation, first order variational problem like this for a function u from some interval a, b, 2 with k components. And this Lagrangian is defined up to a divergence equivalence. So we have some paths, and we see that they are, in some sense that we're gonna say, they're variational, meaning that they remember that they arrive as extremal curves of a variational problem like this for a Lagrangian defined up to this relation. So this is a geometric structure on manifolds of certain dimension. So this is a pretty old problem. Many people have worked on it, but what we have done here is that we solved the equivalence problem for this geometry and say that their fundamental invariance, it has 4 components. So again, I'm being very imprecise and hand wavy, but later we'll see by fundamental problem, meaning that if they vanish, you have something flat. For instance, flat conformal structure, flat Riemannian, flat projective structure. So these structures are in fact richer. They just don't have one component, let's say like conformal structure, you just have Weyl curvature or Riemann tensor. You have 4 components independent. One of them is a cubic, one of them is a bilinear symmetric form, one of them is a 2 form, and the other one is a scalar. And they're all defined up to a scale, right? The conformal class is well defined. So this is, I'm going to make it more precise later. Just to tell you, there's a geometric structure, which is the equivalence of Lagrangians up to divergence equivalence, and it has these fundamental invariants without saying what exactly I mean. Now we can state that one of the main results is that variational orthopath geometries, these structures, these Lagrangians up to divergence equivalence, with this invariant vanishing, this cubic vanishing. So this cubic vanishing means that the Lagrangian remembers that it comes from a quadratic cones. The null cones are quadratic. So that's the reason why this cubic tensor has to vanish.
Can you explain the notation about Lagrangian? So this Lagrangian is what kind of mathematical object? So
they are function defined on you can locally define on first jet of R to R K. So the first jet space, if I have chalk. Yes. Yeah, so they're Lagrangian, this is L from J1 of R to RK and R. So the first jet space functions of, jet space of K functions in one variable. These are, usually this is how we define Lagrangians in the, you can locally view them. This space is locally the same as projectivized tangent bundle of a manifold of dimension K plus 1. Sort of locally, if you view it. It's sort of in an affine chart, it can be identified this way. So their extremals foliate the first jet space, the extremal of this variational problem. So it's a function in 2K plus 1 variables. And it's Hessian in these sort of, these K variables is non-degenerate. I'm going to comment on this later on.
Okay.
Is it okay? Okay. So the result is that these sort of variational orthopath geometries, these Lagrangians up to divergence equivalence with this vanishing condition they're all arise from pseudo-conformal structures with an infinitesimal symmetry, right? So if you start with a pseudo-conformal structure with an infinitesimal symmetry, you always get these. Conversely, all pseudo-conformal structures with an infinitesimal symmetry, no matter what, they're null, time-like, space-like, they arise as a process we call quasi-contactification of these orthopath structures. Yes?
So in this Lagrangian formulation, there is no mention of the conformal structure.
No, there's no, because this doesn't see conformal structure yet. Yeah, exactly. Exactly. There's no conformal because this is on the leaf space. Okay. But then in a nice way, it's sort of related to the conformal structure in a way that is not so obvious. Exactly. It arises, it's something downstairs, and in fact, it's sort of a leaf space it can be identified the leaf space of some conformal structure with symmetry. Yeah. So, and moreover, so having a conformal structure, there's this Weil curvature module. That's sort of the fundamental invariant of any conformal structure. And this Weil curvature module is, in fact, which I'm not going to explain in detail, is sort of almost like a pullback of this fundamental piece of these geometric structures. So you have these geometric structures downstairs, and you're relating the differential invariance. So this has to vanish downstairs if it comes from a conformal structure. This would be pullback to sort of generates almost this piece, the Weil curvature of the conformal structure. And there are these two components that control other things. For instance, if this Q and this A vanish, then you know what you get downstairs is a conformal structure with symmetry, and the symmetry is null. So this is it. This is all set of conformal structures with null infinitesimal symmetry. With null infinitesimal symmetry, they are these sort of structures for which these two invariants are zero. So that's all of them. If, for instance, three of them vanish, A vanish, Dn, and Q vanish, then you know it has a null symmetry, and the orthogonal hyperplane distribution to this null direction is also integrable. So it's orthogonal, it has an orthogonal foliation, this null symmetry. So these three vanishing conditions exhaust all this class. Null symmetry that are orthogonal with an orthogonal foliation. If these vanish and there's a first order condition on this invariant T that I'm not going to write down, then you know that the conformal holonomy of this conformal structure is reduced to a subgroup of the contact parabolic group in the appropriate orthogonal group. Again, what I want to say is that there's a hierarchy. Symmetry, null symmetry, orthogonal foliation, with an orthogonal foliation, here reduced holonomy, conformal holonomy. And the last one is that these two vanish, then in fact, it has a finite moduli, the set of such variational orthopath geometries with this vanishing condition. It depends on finitely many parameters, and they correspond to flat pseudo-conformal structures with a choice of infinitesimal symmetry. So that's sort of, there are 6 of them, but I'm not writing all of them because these are the ones that I think are the most interesting ones. So this is the result, and we're going to just show how to obtain them. Until what time do I have? 40 minutes. I have 40 more minutes. Okay. Okay, so let's start with, again, viewing things as Cartan geometry. It might be helpful for us. So a Cartan geometry, this is not crucial, but it'll help if we use this language. Cartan geometry is a way of, describes a geometric structure that is a certain curved analog of some homogeneous model. So you have these homogeneous spaces, and you want to curve them up. So, for instance, if you want to model conformal pseudo-Riemannian structures, the homogeneous model you want to start with is the quadric of signature PQ, if your conformal structure has signature PQ, which you can view as a homogeneous space where G is orthogonal group of this signature, P plus 1, Q plus 1, and H is the first parabolic, meaning that it's the subgroup in here that preserves a null line. So because here you have an inner product, and with respect to that inner product, you consider the subgroup that preserves an inner a null line. So this quotient space, this homogeneous space, it would be the quadric of signature PQ. So this is, let's say, for conformal structures, this is the flat model, and you want to curve it up. So how do we curve it up? We say a conformal geometry of certain type GH, like in this case, is a principal H bundle. So it's a bundle, and the fibers are the subgroup H, denoted by this curly G over a manifold M, and a Cartan connection. So this Cartan connection is a one form on this bundle, taking value in the Lie algebra of G, this G. It has three properties that basically every tangent space of this bundle can be identified as a linear isomorphism with the Lie algebra. There's an equivariancy condition, meaning that if you move along the fiber, things are transformed nicely. And if you take any sort of fundamental vector field in this fiber, which are this principal H bundle, they satisfy this property. So these three properties are quite nice. It'll really give a nice geometric picture. Instead of working on M, on the manifold M with a conformal structure, you cook up this principal bundle and work on this. This has, for at least the way we did things in this paper, it really helps with figuring out how to descend and how to get geometric structures. So having this one form, we define a curvature that is a two form defined on this principal bundle taking value G. So G value two form. Defined this way, so this psi is the Cartan connection, and it is semi-basic with respect to this fiberation. So it's a two form, and the two form only involves those that are horizontal or semi-basic with respect to fiberation. So some one forms that are not vertical or some not vertical or semi-basic or horizontal there. So if this curvature vanishes, that means the manifold locally isomorphic to the homogeneous model. So this sort of curvature, in fact, controls the sort of deformation, how much it sort of obstruction to flatness of the geometry. So in the case of conformal structures, so of signature PQ, we have a metric of signature PQ. This is the conformal class, so up to a scale. For a pseudo-Riemannian metric of signature PQ, the Cartan geometry, as we said, it's of this type, and this one form, Cartan connection we talked about, can be written this way. So this is a matrix that takes value in the Lie algebra of the orthogonal group. So this is sort of orthogonal value. And if you take these one forms here and cook up this bilinear form and take any section of this bundle. So G is a bundle over M. And now take a section and take the pullback of this bilinear form. So then you would get sort of something on M, on the manifold M, and it is exactly the conformal structure you started with, given in a diagonalized coframe. So these coframes here, these one forms you appear here, sort of they diagonalize. It's a coframe that diagonalizes the conformal structure, the conformal class. So, so here I'm saying what I'm talking about. These epsilon ij are sort of diagonal matrices with p1s and q minus 1s. And this is orthogonal valued with respect to this bilinear form. And in fact, conformal structures, again, they can be viewed as parabolic geometry. They're among parabolic geometries. What it means is that G, which is this guy, is a semi-simple Lie group, and this H is a parabolic. So when you have a Cartan geometry of this type, they're referred to as parabolic geometry. They have very nice properties that we can work with. In particular, in this case.
Excuse me, may I ask a question?
Yes.
What is N with respect to PQ?
What is?
N, small n.
Oh, N is P plus Q.
Okay, thanks.
Yes, sorry, I should have. Yeah. So if you have the Lie algebra, because it's parabolic, it actually, as a parabolic geometry, there's always a splitting of the Lie algebra in sort of a symmetric way, -1 graded and 0 and 1, where you can always view this sort of non-negative part, which corresponds to exactly this diagonal part and these one forms here. These correspond to the Lie algebra of the fiber P1. Remember, this is like G over M is an H fiber, H bundle. So you can view this part of the Lie algebra in this grading, viewed in terms of the matrix-wise, viewed in terms of these one forms as the Lie algebra of the fibers, and the negative part would be the tangent space of the manifold M at each point. So it has these sort of nice properties that we're going to mention sometimes, but it's not necessary for the work we're going to talk about. So now we're going to look at the curvature. Curvature is defined this way. So take this matrix and form this. And there's a theorem in conformal geometry that it's always possible to make, that it's always turns out that the Cartan curvature can be put in this way. So these are two forms. So this is two form put in here. This is a two form. This part will be 0 when you take the d of this, 0, 0, 0, 0. Here you get a two form of this form. And these are in terms of omegas. So that's why it's semi-basic, because remember, we identified these omegas descend to one forms on M. So these are horizontal in terms of omegas. These two forms can be written this way for some psi. Psi is psi.
There's also capital.
Capital. Oh, yes, these are phi. I'm very sorry. Yes, yes. These are capital phi. Yes, yes. So these sort of two forms, and these coefficients are referred to as Weyl curvature. And these coefficients here are referred to as Cotton-York tensors. So this is how you get Weyl. But if Weyl is 0, then these CIJKs are also 0. So this is this is why this is called fundamental invariant or conformal structure. If this is 0, everything is 0. This curvature is 0. So your structure is locally SO mod out by P1. So this is just a brief sort of crash course on Cartan geometric point of view in conformal geometry. I just wanted to show you how you get the Weyl curvature as the fundamental invariant in conformal geometry viewed as a Cartan geometry. Okay, so to do what we want to do, I'm going to just explain the 5 steps we saw before. Each slide would be one of the steps. Yes, 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 yes. So it's one-to-one correspondence. So if you have a conformal structure, it always determines a unique sort of principal bundle like this. And if you start with a principal bundle like this, with a Cartan connection, it determines unique conformal structure on the base.
Okay, can you show once again? Oh, I see. So it says 0.
This is the torsion-free part. It basically exactly means torsion-free. This part is also 0, and these are the Weyl curvature. Yes, yes. Yes. So let's. Okay, the first step, remember, was to see how the sky bundle, the geometric structure on the sky bundle of a pseudo-conformal structure. So now we are working on n+1 dimensional manifolds for reasons that, because we want to take a leaf space, so I add this +1 of signature P+1, Q+1. So this is strictly pseudo-conformal. So P+1 plus Q+1 would be the dimension n+1. This is to make sure it's a non-degenerate metric. It's a pseudo-Riemannian metric. And the metric can be put always, we can find a coframe with respect to which the metric can be put in this way. The conformal class is the conformal class of this form. And epsilon AB is diagonal, P1s, Q-1s. So this metric has signature P plus 1, Q plus 1, and strictly pseudo-conformal. So the sky bundle, as we defined, is the bundle of projectivized null cones. It has dimension 2n, and the fibers are quadrics of dimension n minus 1 at each point, where each sky is defined by the set of direction, the set of lines in the tangent space of each point where they're null. So such a bundle, the sky bundle, has two obvious foliations. One of them is by lift of null geodesics. So what is null geodesics? You have null directions, and in any pseudo-conformal structure, there's a unique geodesic passing through each null direction. So the set of null directions is foliated by the lift of null geodesics. So there's a foliation by curves. This bundle is foliated by curves, which are the lift of null geodesics. Moreover, it is a bundle. Here, this is like a fibration. So there's fibers of dimension n minus 1. So there are two distributions that are actually transversal to each other. The null geodesics and the vertical fibers of this fibration. These two distributions, one of them rank 1, one of them rank n minus 1, they induce a filtration in the tangent space of the bundle in the following sense, that first of all, they are transversal. They intersect only at 0. So this is the vertical tangent bundle of this fibration, and this is the line bundle coming from lift of null geodesics. If you take the Lie bracket of them, you would get something of rank 2n minus 1, right? If you count, it gives a rank 2n minus 1 always. So this is defined on a 2n dimensional manifold. So it's co-rank 1. And this is what we call quasi-contact structure. This is defined this way. And if you take another Lie bracket, you would recover the entire tangent bundle of this fiber. So this is this filtered geometric structure induced on the sky bundle. So the growth vector, this has rank n. It derives into something of co-rank 1 and then rank 2n. But let's see how this co-rank 1 distribution looks like. It's actually quite nice. So if you have, just a simple demonstration, if you have, let's say, your null cone at a point, you have a null cone, right? You go to the sky bundle. Let's say this ray, okay, corresponds to a point in the sky bundle. So this is the ray, let's say, at the point x, and this is the ray that corresponds to y. So x and y, right? So this is the point, sort of ray that we, along y. And so this is a point in the sky bundle. It's a tangent direction and at a point. So hook y, so the point at x, we have point at x, hook y into it, you get a 1 form. And then pull it back to the sky bundle, you get a 1 form. And that 1 form, the kernel of that 1 form is a co-rank 1 distribution and is this H. Alternatively, if you start with this upstairs, this H, and push it forward, push it down on M, you would exactly get this sort of tangent plane to this cone that is tangent along this ray. So it's very natural that there is a co-rank 1 distribution upstairs. Yes. So this H is in fact maximally non-integrable. It's almost like as non-integrable as you can be, but it's on an even dimensional manifold. So in an even dimensional manifold, the non-integrable co-rank 1 distribution, so it has rank odd, so it has to have a degenerate direction, a characteristic. If you restrict the differential of this 1 form to this rank odd distribution, it's a 2 form on an odd dimensional vector space. It has to have a characteristic. It has a degenerate character. So if alpha is the annihilator of H, it has this maximal rank condition, and there's a characteristic, meaning that a vector field on H that sort of, if you plug it in D alpha, you get 0. It's a characteristic direction of alpha. And there's a non-degeneracy condition, meaning that if you start, remember there's a fibration here, there's a fibration. So take the vertical tangent bundle of this fibration, take 2 points, V and W in this V, and then form this. So take the Lie bracket of W with L, and then another Lie bracket with V. This has to lie, because of this filtration, this has to lie outside of H because of being maximally non-integrable. So it gives something in TC mod out by quotient. This is a line bundle, TC mod by H. So it defines takes value in a line bundle. So in fact, and it's symmetric. If you use the Jacobi identity, it's symmetric with respect to V and H. So it determines a symmetric bilinear form on the dual of V of signature PQ. So in fact, what we have done, this H is nothing but the second fundamental form of this sort of, it has to do with second fundamental form of this cone. There's there's a quadratic cone, and now we get sort of a bilinear, symmetric bilinear form, and this is of signature PQ. So it is sort of the second fundamental form of the projectivization of this cone. So in fact, now we have everything. Instead of working with conformal structure on M, we have identified a geometric structure on the sky bundle. Instead of working with a metric, we work on this filtered structure plus this little gadget here. So this is very rich and allows us to now go to the second step. The second step is that the transversal vector, the conformal Killing field lifts to a vector field. First of all, it will be an infinitesimal symmetry of the sky bundle, the sort of geometric structure induced on this sky bundle. And it is transversal to this corank 1 distribution. This is key. That's why we had to look at this quasi-contact structure. So here, I'm just denoting, remember, I had the Cartan connection before. I have omegas here before that were sort of semi-basic, and here this span is usually, so this is sort of we had previously when we were reviewing conformal geometry, these were semi-basic, and here we had the fiber. But now, because we're working on a larger space, the sky bundle, we have more. Not only we have these omegas, which are semi-basic defined on M, we have something else that corresponds to the vertical tangent bundle of the fibration, sky bundle over M. And these are these guys. So we have the sort of three-step fibration. Here we have this distribution. Lie bracket would give a second, T minus 2, and another Lie bracket gives the entire tangent bundle. Here we see it in this matrix form. This is the dual to the vertical. This is the line bundle, the lift of null geodesics. You get the Lie bracket of them, you jump here. So this would be H, all these vector fields would give us H, and then another Lie bracket will cover the entire tangent bundle of this sky bundle. So this was the sort of, we have, instead of a 1 grading that we had in the conformal geometry, now we go to the sky bundle, we get a 3 grading. This is just in terms of Cartan geometries, maybe it's interesting for some people. So they are the Cartan connection is now of a different type. It's not orthogonal on P1, it's orthogonal P1, 2. There's a smaller parabolic subgroup because we're working on a larger space. So now we want to show that the conformal Killing field, meaning this, lifts to an infinitesimal symmetry of the induced structure on the sky bundle. So let's call the lift, this infinitesimal symmetry, as capital Z. So it is an infinitesimal symmetry of the sky bundle, naturally. So it respects the filtration of the sky bundle, the filtration we had on the tangent bundle of this sort of 3-step filtration. So now we want to show that it is transversal to this corank 1 distribution. Assume it's not. Assume that it lies in the corank 1 distribution in an open set. Okay, then if you take any tangent vector to this corank 1 distribution, it follows that because this is on the So because this is an infinitesimal symmetry, the Lie bracket preserves, it has to, the infinitesimal symmetry preserves the grading. So if you have an infinitesimal symmetry, you take the Lie bracket with this, it has to stay in T-1 because it respects the grading, an infinitesimal symmetry. Also, if you take Lie bracket here, it respects the grading, it stays here. So if you start with a vector that lies in H and you take the Lie bracket, it has to stay in H. So it's in the kernel of alpha. Now write it differently, write it in this way, that means this quantity has to be 0. So in other words, Z has to have this property for all elements in H. That means Z is a degenerate direction of alpha. So alpha, because remember, there was this characteristic direction. So Z has to be, as an infinitesimal symmetry, in the characteristic, it has to be the characteristic direction of alpha. But then you will see that characteristic direction cannot respect the filtration, because if you take the Lie bracket of characteristic group, anything in the V, we saw, so if you, this is the characteristic, and you take the Lie bracket, you jump here to -2. So it cannot possibly, so the assumption, it cannot be true. So this cannot be true in an open set. So we get a contradiction, and it has to be transversal to the quasi-contact distribution almost everywhere. So this is a very simple sort of proof by contradiction. Maybe at some points, singular points, it lies in the quasi-contact distribution, but in almost everywhere, it is transversal to it. Okay, now we have a symmetry of this bundle transversal to this co-rank 1 distribution. We go to its leaf space. So the leaf space of the integral curves of the symmetry, we can identify the tangent space to this leaf space with this co-rank 1 distribution, right? It's just natural identification. Okay, now there's actually more. So this is obvious that the leaf space, the tangent space, can be identified with this H, but there's more. So take any quasi-contact form. So we have this co-rank 1 distribution, take the annihilator and choose it because Z is transversal to H. So there is a choice of alpha quasi-contact form so that alpha of Z is equal to 1, is always, because it cannot be 0. It's non-zero almost everywhere. So choose one that is 1. Then we'll see that for all V in this quasi-contact distribution, we have, this is what we saw before, because it's infinitesimal symmetry, this has to be true, then this is true, then that means the inclusion of Z in D alpha is 0, just writing this differently. Now, if you think about this, because of this condition and Cartan identity, you would see that this means that the Lie bracket of D alpha along Z is equal to 0. And now this is a sort of a classical result that once you have this, the Lie bracket of something along certain curve, if it is 0 along the vector field, that means D alpha is a pullback of a true form that is defined on the leaf space of the integral curves of Z. So this sigma, where this two form is defined, is the quotient map of the leaf space. Is a quotient map, this is a quotient map which defines the leaf space of this Z, this sort of infinitesimal symmetry of the sky bundle. So now we're going to the leaf space, and the leaf space has a two form. Okay, so this is a true form defined on an odd dimensional manifold. So it's not a symplectic structure. Symplectic structure is on an even dimensional manifold. So we call it a quasi-symplectic structure. And it is defined up to a scale. Because here we chose this, we imposed this condition, but a priori, it's not defined up to a scale. There's no scale defined. So this two form is defined up to its conformal class is well defined on this leaf space. And it has a characteristic direction because this D alpha had a characteristic upstairs. So this rho also has a characteristic, and it's exactly the push forward of this characteristic direction upstairs. So remember, the characteristic directions upstairs, they were lifts of null geodesics to the sky bundle. Now we're pushing everything down. So these null geodesics become characteristic directions of some two form defined on this leaf space. So the tangent space at each point of this leaf space now can be identified with H, this corank 1 distribution. And now it has a natural filtration. Remember the three-step filtration we had before. Now the last one is gone because we're going to the, truncating at the last step, the transversal direction. We have just these two steps. So this would be L1, the push forward of L line bundle. We have, again, this sort of splitting. Upstairs we had it. We push everything down. And then the Lie bracket gives the entire tangent space to this leaf space. And moreover, this sort of bilinear form we had upstairs also descends downstairs. So we get a bilinear form, again, defined up to a conformal. Remember this bilinear form that sort of remembers the second fundamental form of these cones. So this also is pushed down downstairs. So what do we have so far? We have this leaf space. It has a filtration like this. It has this sort of degenerate conformal structure, sort of a bilinear form defined up to a scale, and it has a closed two form. Now we want to identify what type of geometric structure it is on this leaf space. This means the rank. Sorry, I mean like L1 meaning like it's a rank. Sorry, yes. So it's a push forward. Everything is pushed down by this quotient map. Yeah. Oh, this shouldn't be pi. This is, I think I saw this is tau. This tau that sort of defines the leaf space. This is tau. Yeah. So the quotient map. Okay, now this is, in fact, we want to see, okay, what this geometric structure is on this leaf space. And this is actually the easy part because we basically, again, by very unfortunate accident, we stumbled upon these works that what we have done exactly fits into them. So remember that we have this two-step filtration and this sort of bilinear form and a two form. So this filtration that we had before, it sort of is something that defined that it is called sort of a generalized path geometry. So this filtration gives a sort of path geometry on, and what it means is that, what is a path geometry? You have a manifold and it has a family of curves such that at each point along each direction there passes a unique path, like geodesics of a Riemannian metric. So it is modeled, again, it's a Cartan geometry. It's modeled, what's the local model? What's the flat model? It's Pn. The projective space, it has projective lines. So if you take projective space and take its tangent bundle and projectivize it, so projectivize tangent bundle of Pn, the fibers are Pn minus 1, projective spaces of dimension n minus 1. And they exactly can be curved into for any other manifold. So you have a manifold and then go to its projectivized tangent bundle, and the fibers are projectivized tangent spaces. And it turns out if you have a path geometry on n, meaning that at each point along each direction there passes a unique path, like geodesics of a Riemannian metric, then the curves foliate, the natural lift of curves foliate the projectivized tangent bundle in a way that they are transversal to the fibers, right? You have a path geometry, geodesics of a Riemannian metric, lifted to the projectivized tangent bundle, and the lifts are always transversal to the projectivized tangent spaces. In such a way that if you take the Lie bracket of the lift and the fibers, you get the entire tangent space, the entire tangent space at each point, to the Lie bracket. So this is path geometry in a nutshell. But we have something more. We define a notion of orthopath geometry, path geometry with a bilinear form. This is the bilinear form we had before. So it's a bilinear form that is defined on sort of this would be the vertical tangent bundle with respect to this fibration. So this is a natural fibration in any manifold. And there is this tangent at each point in this tangent bundle, there is a non-degenerate symmetric bilinear form defined up to a scale. So this is the augmentation of the path geometry. As soon as you have a path geometry with such an augmentation, with this additional tensorial object defined here, this sort of reduces the so-called, if you're not familiar, it's not really crucial for the rest of the, it sort of defines, you have a path geometry and an augmentation, it reduces the structure group of the geometry, and you can naturally define a two-form on the manifold. The two-form may not be closed, may not have a closed representative, but you can always define a two-form. And these the two forms, they always have a characteristic, and we assume that there's a compatibility condition, that the characteristics of this two form are the paths of this path geometry. So this is exactly, I am basically rephrasing as an abstract geometric structure what we had in the previous slide, what we ended up in the previous slide. But then with the works of Griffiths, Philip Griffiths, he has a book in the 80s or 70s, I don't remember, and Ian Anderson's works on variational bicomplex. Immediately seeing this geometry, you would realize that they have something to do with problem of calculus of variation. So we call them, yes? No. It's only when you define this that it has.
Okay. So it's part of the augmented.
Yes. So once you add this sort of bilinear form, then this two form also appears. Or you can go the other way around. Augmented with a two form like this, with this condition that the characteristics of the two form are the paths and some compatibility condition, then this one appears. Sigma would be, in this case, would be exactly, so you had this sky bundle, and then you go to the leaves. So the sky bundle has an infinitesimal symmetry, right? Because we started with a conformal structure with a conformal killing field. Then we went to the sky bundle, right? The sky bundle of the conformal structure. Then the sky bundle naturally has an infinitesimal symmetry too, the lifts of this conformal killing field. And the sigma is the leaf space of the sky bundle with respect to the integral curves of the infinitesimal symmetry.
And so, and this metric tensor H, can I think of it as a metric tensor?
But it is a metric tensor on a distribution. It's not on the entire sigma. It's on a sort of a, because sigma, you see sigma here, sigma has on each tangent space, it has a line field and a rank n-1 distribution. This H is defined on this distribution, integrable distribution. Yes, there you can do that. Yes. Yeah, it's very canonical, easy to relate things. Yeah, this is what we do in the paper. Yeah, we're gonna get there too soon. Yeah. So, what happened? Okay, so we say it's. Yes, so it's not. It means that this sort of class of two forms, they may not have a closed representative. Yeah, it is closed. Yes, because you see in the construction when we had, rho was D of alpha was the pullback of a rho. So naturally, rho has to be closed.
Okay, so now. Right?
Yeah. So now we want to see. The thing is, we know that if we start from a conformal structure, we go downstairs to something that has a two form that has a closed representative. So it's actually not, they cannot be almost, right? So we call a sort of orthopath geometry. This is an orthopath because orthogonal path geometry. So there's this bilinear form. And we call this a orthopath geometry variational if this conformal class of two forms has a closed representative. This is the definition of variational orthopath geometry. And now this is sort of. Yes. Ian Anderson, yes.
Which one?
Ian Anderson in Utah, Utah State. Yes, the famous one. Exactly, Maple and exactly. I mean, he's a student of Lovelock, so he worked on variational calculus, in his PhD, and after that, and also Griffiths sort of independently have a different approach in a book that is not quite well known, sort of calculus of variation in exterior differential systems. And using these two, you would see that this geometric structure we get, immediately you realize there's a connection to calculus of variation in the following sense. So this is really from just a theorem from Anderson's book with Thompson in the 90s. They have a very nice book. They say that once you have this structure that we defined here, I'm not going to go into the, we're, I think, over time even right now. Yeah, almost. So once you have this, Anderson tells you that sigma, this leaf space, so sky bundle, go to the leaf space by the integral curves of the infinitesimal symmetry. This sort of sigma can be identified locally as the first jet of functions, n-1 functions, one variables. And additionally, rho, this two form, is the vertical exterior derivative of a one form eta. So in a jet bundle, you have the sort of vertical exterior derivative and horizontal exterior derivative. We won't have time to go through this. So this rho can be written as dv of some one form, where this one form is written this way. So these are coordinates on the jet space. So x and yi and pi's are sort of fiber coordinates of J1 over J0. So eta can be written in this one form where this L is exactly this Lagrangian that we need. So L is a Lagrangian with non-degenerate Hessian. So it's a Hessian with respect to pi variables is non-zero, is non-degenerate. So L is a function defined on J1 to R. And because you see, we don't have a well-defined one form. We only have like a conformal class of two forms. So this Lagrangian, we don't have a distinguished Lagrangian, but in fact, we just have a Lagrangian up to multiplication by constant and addition of a total differential. So this is basically this variationality of the problem just comes from works of, really huge body of work of other people. So this is how we get the Lagrangian. And so this Lagrangian, you can think about it as appearing from, a Finsler structure, pseudo-Finsler structure, or a Riemannian structure. So this sort of is a way of measuring length of vector fields. So it's a norm at each tangent space. So it might be Finslerian, might be Riemannian, it's not known. But the last thing is that we sort of, now this is a geometric structure. We want to find so far what we have found. Pseudo-conformal structure with an infinitesimal symmetry are in one-to-one correspondence with variational orthopath geometries, but with not all of them. We just talked about all variational orthopath geometries, but which of them come from a conformal structure? We haven't determined this yet. So to do this, we solve the equivalence problem of variational orthopath geometries. So I'm not going to talk about how we do it. So this is, again, a Cartan geometry. So you have a path geometry. It's a Cartan geometry of this type. We actually, when we do this augmentation, this bilinear form, the type is reduced to something else. We don't have time to go through this. So this sort of the Lie algebra, it has one-dimensional prolongation. So this was, remember, the Cartan connection for the conformal structure. And we truncated at the third step. We truncated here, and we get something for the Cartan connection downstairs on the leaf space. It's quite neat in terms of construction. So solving the equivalence problem for this geometries, we find that there are four components in the fundament to determine when this geometries are basically the homogeneous space, meaning the quotient of this Lie group by that Lie group. There's a notion of flatness for these geometries, won't go through. So there are 4 components that control the sort of flatness fundamentally of such geometries, and they're all defined up to a scale. And they're all sort of defined on this vertical tangent bundle. There's a cubic form, there's a bilinear form, and they're all trace-free. Trace-free, a 2 form, and a scalar defined up to a scale. So there's a one function defined, so it's vanishing is well defined. The function defined up to a scale. It turns, yes.
So this
the vertical.
Okay, is that the complement of L with respect to this row?
Oh, it is no. It's sort of Lagrangian with respect to this 2 form.
Oh, yeah,
Yes. But the thing is, it is integrable. So there's a line field, there's a integrable distribution, and the Lie bracket gives the entire tangent bundle. It's like a path geometry. Path geometry, you have the path, and you have the vertical tangent bundle of the projectivized tangent bundle over the manifold. So these are the fibers, the projective. Yeah, it's Lagrangian with respect to the 2 form. Anyway, so it turns out that this is the result, that if this cubic vanishes, the set of such variational problem always arise from conformal structures with symmetry. That's the conclusion. And this is not, not too straightforward to show, but and in fact, we can do a sort of Cartan-Kähler analysis, finding the generality. The generality of such orthopath geometries with this vanishing depends on this many functions of n variables. And then you compare it with conformal structures, sort of coming from a sky bundle like this, locally depend on the same number of functions, but with n plus 1 variables. So this confirms the fact that if you have any geometric structures with symmetry, the generality would remain the same, but when you go to the leaf space, just the number of variables is reduced by 1. So this is quite expected, and this is what we get from this construction, Okay, and we want to go backwards, and we sort of start with a variational orthopath geometry, right? You have downstairs. We want to go now the other way around. So start with a variational orthopath geometry. You have this class of 2 forms. Take a closed representative in this 2 form. So it can be written as D of some 1 form. Take a primitive. Now form this product space. And on this product space, define a new 1 form as dt plus the pullback of this primitive, beta 0. So this t is the coordinate on this r. So now you have a 1 form, and there's a fibration from this sort of product space to your original manifold where this variational orthopath geometry is defined. So now you have a Cartan bundle over the sigma, pull everything back to this product space, the Cartan bundle that you have, pull it back, and you get this product space plus some principal bundle. And it turns out this principal bundle and the Cartan connection you had here, plus this 1 form you cooked up, gives a Cartan connection on this pullback bundle. So you can modify and play around with things to immediately realize this C, this product space that you cooked up, is in fact the sky bundle of some conformal structure with a choice of infinitesimal symmetry, and the infinitesimal symmetry is d dt of this dummy variable we introduced. So this is actually going backwards is extremely easy. Just introduce the product space and then go to this product manifold and introduce it, sort of straighten the infinitesimal symmetry almost.
Could it be the case that product space that canonical, some kind of canonical line bundle?
We tried that. Exactly. We tried that. We couldn't quite. It is in some cases, though. In some cases, but in all cases, we could. Something didn't work. It's more. Yeah. But in some cases, yes. Okay, so this is the theorem we proved. I'm going to bring it here so that we know what we talked about. And just as an application, we see, okay, let's start with orthopath geometry. Let's start with a Riemannian metric. It has geodesics. Riemannian metric with geodesics defines a variational orthopath structure, obviously. So now take this orthopath geometry and quasi-contactify it. You would see that you would exactly get this conformal structure, natural conformal structure I talked about at the very beginning on this product space. So this is, in a way, it is sort of nice to see the most well-known case that you had would come out from this construction, right? So a Riemannian metric defines an orthopath geometry, it's geodesics, obviously, and there is this augmentation comes from the Riemannian metric. So orthopath, the thing is, orthopath structure is not defined. That's exactly why we have to go to the sky bundle. You see, we have n+1 dimensional manner with conformal structure. We went to a sky bundle is 2n, right? Then we went to sigma in this manifold. The thing is, then you can go again to the sort of because these are the vertical, these are the skies. Here, there's also these are the quadrics. These are there's again an integrable distribution here, and you can go to something of dimension n, right? But the thing is, here there might not be a geometric structure, a G structure. It may not. You see, conformal structure is a G structure defined here, but when you go to the leaf space, there might not be a G structure defined here. That's why you have to go to this sort of. This can be identified as projectivized tangent bundle of them. So there's a G structure defined on this space, not on this space. But sometimes things descend in special cases, but not in general. So that's why we have to go to the sky bundle to be able to give the treatment of all conformal structures with infinitesimal symmetry.
So the n would be the space
of the infinitesimal symmetry on M. Yes. So this is one example. The other example is that Pfefferman matrix. Right? So pick your favorite example of conformal structure with an infinitesimal symmetry. A very famous example is conformal structures arising from the Pfefferman construction for CR structure. So it turns out that when you start with any CR structure, it defines the CR structure. They have chains. The chains of any actually partially integrable almost CR structure defines a canonical orthopath structure. And it turns out this sort of orthopath structure that the chains of the integrable, partially integrable, almost CR structure define, this orthopath structure is variational if and only if the almost CR structure is integrable, right? And in fact, such orthopath geometries satisfy this condition. So this means that the quasi-contactification is conformal, like Pfefferman construction, and this Q vanishing means that the conformal symmetry is null. This is what we had in the, and this is again null. So in fact, the quasi-contactification of such orthopath geometries exactly give the Pfefferman construction, the Pfefferman-Lorentzian conformal structure for CR structure. So again, we recover something, and we show that this is a result that recently shown by these people that the chains of a CR structure are variational. So we give a more, I think, more conceptual proof of that. And again, there are other geometric structures like this way you can show the Einstein-Weil structure or the geodesics of an Einstein-Weil structure are variational by work of Jones and Todd. I'm not going to talk about. And lastly, if let's say we start with quasi-contactifying variational orthopath geometries with this quantity not zero. So if this is zero, we know it comes from a pseudo-conformal structure with symmetry. But what if this is not zero? It turns out in this case, then you quasi-contactify them. These correspond to causal structures with an infinitesimal symmetry. So the null cones here, the null cones, they cannot any longer be quadratic. They're not necessarily quadratic. They might be some other non-degenerate projective hypersurfaces. They might be cubic, they might not be even algebraic, but you have a manifold with sort of null cones, Finslerian null cones that are not really quadratic. They don't come from a metric. So we also cover that, not only conformal structure, but causal structure with an infinitesimal symmetry. Another two classes that again, fits into our treatment are 2-3-5 distributions and 3-6 distributions. And in fact, we show that 2-3-5 structures with an infinitesimal symmetry correspond to variational fourth order ODEs under point equivalence. So you just, given any ODE, you can determine when it's variational, if these two are 0. And it turns out that we actually can give all 2-3-5 distributions with null symmetry. They arise from Euler-Lagrange equations, quasi-contactifying fourth order ODEs that are Euler-Lagrange equations of Lagrangians of this form. So this really sort of closed form of 2-3-5s with null symmetry. For 3-6 distributions with null symmetry, they all correspond to variational pairs of third order ODEs. Here, third order ODEs, they correspond to their variational when the Lagrangian is degenerate. So I'm not going to talk about, but these are the other classes that fit into our treatment. But the most famous one was the sort of strictly pseudo-conformal structures that we just talked about. So thank you very much, and sorry for taking so much of your time.
Some questions? No questions, Armand?
So the main point is instead of considering the lead space, it's maybe consider this. I could have that which is called a twisted space. I mean, it's not what it should only be like a twisted space because you would
This correspondence space. And
it's not a twisted space.
No, it's actually very different. But that's actually one of our main confusions at the beginning, that this sort of symmetry reduction that going to this leaf space is different from this correspondence in this twistorial picture. Yeah. So it's completely different. That was really confused that can we view it as sort of some sort of twistorial picture, but no. When you go to the correspondence space and you go to leaf space, it's really a symmetry reduction that you basically truncate your structure. You only get this, yeah.
And I guess the advantage of the standard twisted space is that in the case, the twisted space doesn't have any.
Yes.
In this case, no.
Yes.
So would you simplify problems, variation problems, like constantly then conformal part?
I think it's the other way for me, at least. The conformal with symmetry, now you just only worked with these guys. And then you can actually see what problems such as the following. So what are conformally Einstein spaces with an infinitesimal symmetry? So now we want to look for a theory of almost Einstein sort of divergence equivalence of Lagrangians, what it means. So now this way, there are works actually following Chap and Salach. That was one of their main motivations. So the next step would be something like this, to sort of come up with this sort of these invariant operators for this geometry we get downstairs.
So there is no answer.
No.
Are there questions? If not, thank you again.
Thank you.